Everyone, and thanks for watching Edupedia World videos. I'm Manish Agarwal, and in this session we will go into the details of the topic of equilibrium. We have already gotten a preliminary view in the previous video, but here we'll go into the details of how the equilibrium is established and what does it actually signify. So let's begin. So we already know that the meaning of equilibrium is simply a state, okay, or the time at which the rate of process going in forward direction will exactly be equal to the rate of any process going in the backward direction. That is to say, if you have a container and in this container I started with reactants. Let's take a simple example, say H2 plus O2. So I started with H2 and O2 in my container as reactants. So they will start forming water upon reaction. Alright, so this is your forward direction. Similarly, the water will break down, form back H2 and O2. Alright, so here you have two different reactions. One is the forward reaction where water is being formed. Let's say the rate of forward reaction is RF, and one is the backward reaction where water gets decomposed back into H2 and O2, which is our backward reaction. So let's call the rate of backward reaction as RB. Right, so these rates might have different values at different times. Eventually there will come a time when RF might be equal to RB, and when that comes, when RF becomes equal to RB, we can say that our system, that is the reaction inside the container, is in the state of equilibrium. Right, so the condition on equilibrium, okay, the condition for establishment of equilibrium is only on the rates of forward reaction and rate of backward reaction. That is, rate means it is something like the speed, okay, the speed with which reactant is getting consumed, and the rate of backward reaction can be said to be the speed with which the products are getting consumed back to reactant. Okay, so that is what we mean here by RF and RB. So when these two rates are equal, the situation that is present is called the equilibrium. Okay, so this is how it is established. So be sure that here the condition for establishment of equilibrium is only on rate. There is no as such condition on the concentrations of reactants and products. Okay, though it might be that at equilibrium the concentrations can have certain conditions, certain constraints on them, but they are not inherent to the definition of equilibrium itself. So the basic definition, the fundamental definition, is only derived from the rate of reactions in the forward and backward direction, and based on this we might derive some other conditions, some other constraints which can define equilibrium in a much better way. So for now let's only take rates into consideration and forget about anything else like concentrations, pressures, volume, temperature. Okay, let's forget about all of that for now. So let's study the process in further detail. See, what happens is whenever you are making a reaction, a chemical reaction, for your syllabus we can always assume that the reaction is taking place at a constant temperature. The temperature of the container is kept constant throughout your reaction process. Alright, because this makes things easier, okay, to analyze. This makes it sure for us to establish an equilibrium condition in the container by keeping the temperature constant. So let's take a container. In this container I have taken my reactants H2 plus O2. So as soon as I take this H2 and O2 in my container, these two reactants can react and form H2O. The balanced equation can be written in a different form. Okay, we can write it like this. Okay, so this is the balanced chemical equation in which shows that H2 and O2 combines to form water molecule. So as soon as initially only H2 and O2 are there and there is no water, but as soon as the first molecule of water is formed, we can say that under the same experimental conditions in which water is being formed, it is possible for water molecule to break down again, okay, to break down again and form back H2 and O2. That is, initially the reaction was going only in forward direction because there were only reactants, there were only components of left hand side present. Okay, this is the left hand side of our equation, so hence the reaction was only going in forward direction initially. But as soon as there is a product here, okay, this product can now break down and what we can get is the backward reaction as well. And with time what happens is the amount of H2 and the amount of O2 will keep on decreasing. This decrease in concentrations or the amounts of reactants on the left hand side results in decrease in the rate of forward direction, that is the speed with which they are getting consumed, also decreases if their amounts decrease. Similarly, on the right hand side, what is happening is initially there was no H2O. That means there was no backward reaction. That means initially the rate of backward reaction was 0. But with time, the amount of water molecule will keep on increasing because there is forward reaction taking place. And as the water molecule increases, the speed with which this water is getting decomposed will also increase. If there is more water, more of it can get decomposed. If there is less water, only less of it can get decomposed per unit time. So that means your rate of forward reaction will keep on decreasing and your rate of backward reaction will keep on increasing. Finally, there will come a time at which rate of forward reaction will be equal to rate of backward reaction. And when this time comes, the system is said to have achieved the equilibrium. Alright, we can see this whole phenomena using graphical approach as well. So let's try and plot a graph of rate versus time. On the y-axis, I have rate of reaction, both forward and backward reactions, and on the x-axis I will have time or the progress of your reaction is on the x-axis. So initially, if you only look at forward reaction, what happens is the rate of forward reaction starts somewhere from here, okay, because it has some finite value at t is equal to 0 as well. That is when we are just starting the observation. Alright, so at time t is equal to 0 as well, your rate of forward reaction has some finite value because you have some finite amount of H2 and O2 in your container. With time, the amount of H2 and O2 keeps on decreasing because it is getting converted into water. So that is to say, your rate of forward reaction will decrease. Okay, it will keep on decreasing. Similarly, if you look at the rate of backward reaction, what happens is your rate of backward reaction will start from 0. It will start from 0, but as the more and more water is formed, okay, after the first water molecule, as more and more water molecule is formed, the rate of backward reaction will keep on increasing. So hence there will finally come a time here at which rate of forward reaction will become equal to rate of backward reaction. So after this time, what happens is the rate at which reactants are getting consumed, that is the forward reaction, will be equal to rate at which the reactants are getting formed again, that is the backward reaction. Hence there is no more change in the concentration of reactants, hence there will not be any more change in the rate of forward reaction. So rate of forward reaction will become a constant straight line. Similarly, if you look at the product side, after this time, okay, let's call it TEQ, the rate of backward reaction is equal to rate of forward reaction. That means the rate at which water is getting consumed is equal to the rate at which the water is getting formed. Hence there will not be any more change in the concentration or the amount of water molecule as well, because of which rate of backward reaction will also become constant. That is, after TEQ, after this time, rate of forward reaction has become constant, and rate of backward reaction has also become constant, and since they are both equal, you can say they will both move in a straight line together. Okay, so what has happened over here? Initially rate of forward reaction kept on decreasing, rate of backward reaction kept on increasing. Finally, after time TEQ, rate RF was equal to RB, and it continued to be so for eternity. Okay, so during this state, all of this state starting from TEQ, your system has achieved equilibrium, and it will remain in this state of equilibrium as long as you do not disturb the system externally. So unless you bring about some external intervention, alright, the equilibrium state will continue to exist the way it was existing before. And this time TEQ is said to be the time, okay, the time at which equilibrium was established. Okay, so that is why we are referring it to as TEQ, that is time for equilibrium established. So this is how the rate graph looks for forward and backward reaction. So ultimately both the rates will have to become equal and constant for equilibrium to exist in your system. But there is no such condition on the concentrations. Let's try and plot a graph of concentrations over here. So if instead of rate I have concentration, that is to say, let's say molarity of your reactants and products versus time. So initially the amount of product present with me is 0, water is 0, and the amount of water will keep on increasing. Finally, after time TEQ, we know that rate of consumption of water is equal to rate of formation of water. That means there will not be any more change in the amount of water. so it will become constant. So this is how the amount of product or the molarity of product or the concentration of product looks like. Similarly, if I try to plot a graph of concentration of H2, okay, and concentration of O2, let's say initially they were here. So amount of water will keep on decreasing, and it will keep on decreasing up to time TEQ, after which it will also become constant, because rate of forward is equal to rate of backward, that is rate of consumption of O2 is equal to rate of formation of O2. Similarly for H2, the amount of H2 will keep on decreasing, and finally after time TEQ it will become constant. That is to say that the concentrations of reactants and products upon establishment of equilibrium all become constant, but they are not equal. They can be equal. It is possible that all of these three concentrations merge together, okay, in a certain condition, such that concentration of H2 is equal to concentration of H2O is equal to concentration of O2, but that might or might not happen. Okay, it is not a necessary condition. Okay, the only thing that we can decipher here is that after equilibrium I can be sure that the concentrations of every component in my system, whether it is reactant or product, will become constant, and what its value will be, that is something we cannot ascertain over here. Okay, so this is how a system establishes equilibrium. So it is quite important that you understand both these graphs of concentration versus time as well as rate versus time, and you also understand the difference between them, that the rate of forward will become equal to rate of backward, but there is no such necessary condition on the concentrations of left hand side and right hand side. They can be equal, they might not be equal. So let's move ahead and look at some more characteristics of equilibrium. See, the first point about equilibrium is that it can be achieved from either direction. That is to say, instead of starting from reactants, I can also start from products and establish the same equilibrium in my container. Measurable properties of the system become constant under given experimental conditions. That is to say that once the equilibrium is established, this is all for equilibrium conditions. So at equilibrium, all the measurable properties, for example concentration of your reactant or concentration of your product, they become constant, right? That is, as long as the experimental conditions are not changed, that is pressure, volume, temperature, all these are not changed. The measurable properties like concentrations, maybe say density of your system inside the container, or maybe refractive index of your system inside the container, all these values will not change, okay, unless you are making some kind of external intervention. They become constant. Also, a very important point over here is that the equilibrium is always dynamic in nature, and hence it is also called quasi-static. Quasi means it is not actually static, but it looks like the system is static, that is, it is not changing anymore, there is nothing happening over here, but in reality the equilibrium is always dynamic in nature. Let's go into the details of all these 3 points. Let's look at what do they actually mean for us. So see, basically when I say that equilibrium can be achieved from either direction, what I mean is that instead of starting from H2 plus O2, I can also start my reaction from H2O. So this means H2O is now going to break, alright, it will now break to form H2 plus O2. So balancing this reaction, this will be how the reaction will take place. As soon as first molecules of H2 and O2 are formed, so it is possible that they might combine again to form water. That is, my backward reaction will also start taking place, and eventually there will come a time when here once again rate of reactions in both the directions will become equal, and at that moment I can say that my equilibrium has been established. So here, instead of starting from the left hand side, I started from the right hand side and then established the equilibrium. That is what we mean by saying that equilibrium can be achieved from either direction. Okay, the next point, that all the measurable properties become constant, this you will understand more as we go along with the chapter, but for now you have already understood that the concentrations become constant, that once equilibrium has been established, that is time is equal to TEQ, after this time concentration of H2 like molarity or mole fraction, okay, any property like pressure, partial pressures, all of them will become constant and they will not change anymore. Similarly, if I measure density of my system, that inside my container I have mixture of three gases, H2O2 and H2O, so I can measure the density of this mixture of gases, rho. Alright, and this density will have a constant value and it will not change with time anymore once the equilibrium is established. Up till the point equilibrium was not established, the density, the concentrations, they kept on changing with time. But once TEQ has been reached, alright, there will not be any more changes in such physical properties of the system. Last point, that the dynamic nature of equilibrium, let's analyze that in greater detail. Okay, because it is a very important point and you often get questions based on that in both JEE mains as well as JEE advanced. One common type of question is, let's say I have an equilibrium between H2O2 and H2O. Let's say if my equilibrium is present at this moment. Initially there was no equilibrium. Initially T is equal to 0, amount of water was 0, and I only had, let's say, A moles of H2 and B moles of O2. At T equilibrium, let's say I will have different amounts. At T is equal to T equilibrium, amount of H2 is C moles, amount of O2 is D moles, and let's say moles of H2 or amount of H2 is E moles. So once equilibrium has been established, the concentration is now C, D and E, and it will remain to be so without any change. So does that mean the reaction has stopped? Does it mean there is no more forward reaction and there is no more backward reaction taking place, and that is why all the concentrations have become constant? So no, that is not true. Alright, we have already seen that concentrations are constant because RF is equal to RB, because of which the rate of consumption of C and D is equal to the rate of formation of C and D, and hence there is no net change in the values of C and D. Similarly, for E, there is no net change in the values of E. Okay, but both the reactions, that is both forward as well as backward reaction, is still taking place, and hence we say that though everything seems to be static, all the measurable properties are constant, okay, even then the reaction is taking place, and hence it seems to be static but it is not actually static, and such systems are thus called quasi-static. Okay, or we also say that the equilibrium is always dynamic in nature. So one type of question is that if instead of H2 now at TEQ, okay, at this time, if I introduce, instead of H2 I introduce, say, deuterium, an isotope of hydrogen, alright, D2 in my system, alright. So replacing H2 I have introduced D2. Okay, so what this means is, instead of having C moles of H2, I have somehow now managed to get rid of all this H2, and instead of H2 now I have D2 in the same exact amount, that is C moles of D2, which are reacting with O2 in D mole quantity, and there is water present in E moles quantity. So since the system is at equilibrium, there will not be any change in the values of C, D and E. But okay, as the time goes on, we can use a mass spectrometer to determine that the composition of your system has changed, because the reaction is still taking place. If the reaction was not taking place, D2 will always be in form of D2, O2 will always be in form of O2, and H2O will remain in form of H2O. But it so happens that mass spectrometer reveals that though the total amount remains same, C, D and E, the composition changes. That is, now if I come back after some time and analyze my system, I find that I have D2 in my system, as well as I have D2O in my system, as well as I have DHO in my system. How is this possible? This is possible because some deuterium reacted with oxygen to form D2O. So it is just like H2O. It is just like H2O, but instead of hydrogen, I now have deuteriums attached to my oxygen. Similarly, the H2O which breaks down will form O2 and H2. So this existing H2O, when this will break, say it breaks over here, so this will give me H2 and O2. Hence, I can also find some hydrogen in my container again. Though I had replaced all of the hydrogen with deuterium, because of hydrogen in H2O, after some time I can still find hydrogen present in my container. And this hydrogen can combine with oxygen, while simultaneously a deuterium combines with oxygen, leading to the formation of something called DHO. So it is again water, but water with one hydrogen being replaced by deuterium. So this is possible that I have different isotopes of all the substances. Okay, so instead of D2 I also have H2. Instead of H2O I also have DHO and D2O in my container, and H2O also being there. So this is possible only if my system is still dynamic, that is forward and backward reactions are still taking place, that is breaking and formation of bond. So that breakage and formation is still going on, and hence we say that the system is dynamic in nature. So this is a very important point which you must remember. Later on we'll also, okay, towards the end of the chapter we'll also make changes in our system once the equilibrium is achieved, and because the reactions are still going on in both forward and backward direction, we'll try and analyze the result of those changes on our system. So until then, and once again, thanks for watching Edupedia World videos.